Hello children, how are you people doing? I'm Saurabh Kumar Dutt and I'm here to teach you people a little bit of mathematics, wherein today we are going to discuss heights and distances. Now this is a topic where we'll be dealing with the angle of elevation, the angle of depression, and further we'll also be trying to equip all of this in a right angle triangle so that the trigonometric ratios can be applied, and further you can find out the necessary heights and distances using the heights and distances which have been given to you in the question. So children, here first we'll be discussing the concept, and after that I will give you a special question. I'll give you a little time to try, and after that if you're not able to do it, I'll help you with it and ensure that everything is very well understood. So this topic of heights and distances, which is in trigonometry, is next now going to be considered, and for that matter I will take your example. Let us say you are Alan, okay, and let's say that you are standing at the top of a building and you're trying to see something which is fallen on the ground. For that matter, let me quickly make you be placed on the top of a building. Let's say now that this be that very tall building and you are standing atop it, and now you are watching something which is at the ground level. So obviously now there's also to be the ground level. So let's say this straight line be the line which actually depicts the ground level. Then further, now as you are standing above on the top of this tall building, so next now we'll be joining your eyes to the object that you're watching. Now I'm not asking you what you're watching, right? But whatever you are watching is with what we are concerned, because that is going to help us in understanding heights and distances, and also the primary concept of the angle of elevation and the angle of depression. So here, if say now we talk about drawing a straight line from your eyes to whatever object you're watching, right? Okay, so this, children, is going to be your line of sight, right? And this line of sight, remember, is the line along which a person watches, right? That means a person is standing on top, and if he watches something below, then the straight line joining his or her eyes to that object that that person is watching is the line of sight, right? I'll rather write it too. So this is the line of sight, right? And here, children, we have this building, okay, and on top of it we have Alan here, right? And in fact this is Alan's eye. Okay, now the angle which the straight line joining the eyes of the observer to the object makes with a straight line drawn from the eyes of the observer parallel to the horizontal, right? So we require another line, that is this line. Now this is that line which is parallel to the horizontal. That means this line and this line are parallel to each other, and the angle between both of these is said to be the angle of depression, right? So what is this? This is the angle of depression. Why depression? That is because you are depressing your eyes. That means you're pressing your eyes to see something below, and that is why this is known as the angle of depression, right? So all of this concept I will just quickly discuss. Here what we have is, we have a friend of ours, Alan, who's standing on top of a building and he's trying to watch something very keenly, right? And when he is watching, then obviously there is a straight line which has been drawn from the eyes of the observer to the object that he is watching, and this, children, is known as the line of sight, right? Now when you find an angle with the line of sight with another straight line which is drawn from the eyes of the observer and is parallel to the horizontal, then the angle between both of these straight lines is known as the angle of depression. Now remember, children, as we have both of these straight lines to be parallel, so obviously we will also be having alternate interior angles. So if you talk about this angle is also theta d. That means it is also the same angle of depression. Now a case which is contrary to this is on the angle of elevation. So when we deal with a concept of angle of elevation in times to come, then we'll discuss it. At this moment, we are going to deal with an interesting question on the angle of depression, and this, children, is that question. So I'll give you people a little time for trial, and after that I'll be discussing the sum. So meanwhile, I want everybody to pick up their pens, put up their efforts to be able to solve the sum. Go ahead. I'm sure you'll feel interested, and then you'd like to try this for a longer duration of time. For that, you can easily pause the lecture and try it for a longer duration of time. Because if you've been able to reach even a little ahead, it's going to give you a lot of confidence, right? So do try. Okay, thinking that you guys have tried it out and now you are actually sweating out, that means there is a little bit of difficulty. So I will explain how the sum is going to go. So here, children, we've been given, as you've seen, that there is a balloon and you have the angles of depression of 2 kilometer stones, which are observed to be alpha and beta. So here, first what we require to do is we require to make the balloon and the 2 kilometer stones, right? And for that matter, then what we do is, now here we get the triangle. Now here I come back to my position, and now, children, here I will be making this balloon along with the 2 kilometer stones. So let's consider that the balloon is atop here, right? And after that, the first kilometer stone is here and the second kilometer stone is here. Now, as these are 2 kilometer stones, so obviously there will be a distance of 1 kilometer or 1000 meters in between them. So let us consider that the distance that we talk about between both of these is actually 1 kilometer, and here we can mark it in this figure, something like this. Now for the children, here you've been told that the stones are on either side of the balloon, right? That's why we made it this way. So we keep the balloon at the center, and if suppose the balloons would have been on the other side, that means on the same side, right, then we would have ensured that the balloon is on one side and both the kilometer stones are on the other side, right? Okay, now after this, next we've been given that the angles of depression of both of these stones are alpha and beta. For the angle of depression, children, what we've got to do is we've got to draw a straight line which is from the eyes of the observer to the object that is already drawn. That means if you talk about this straight line, which is B to S1, this is actually your first line of sight, and B to S2 is actually your second line of sight. Now here further, we require to make a straight line which is parallel to the horizontal, and for that what we do is we will now be drawing a straight line which is going to be parallel to the horizontal. And let's say now, children, that we have that line to be like this. Okay, so this, as you can see, is a line which is parallel to the horizontal, and as such we have both of these lines being parallel to be shown by these arrowheads. Okay, now as the first angle has been given to you to be alpha, so here we can mark alpha to be the angle of depression, as remember the angle of depression is the angle between the line of sight, that is this straight line, and another straight line which is drawn from the eyes of the observer parallel to the horizontal, right? So as such, the angle between both of these lines is your angle of depression, and for the first case it is alpha, and for the second case, children, what is it? It is beta, right? So obviously here again in the same way we'll be talking about this straight line BS2 to be your second line of sight, and its angle with another straight line which has been drawn from the eyes of the observer parallel to the horizontal, right, becomes the second angle of depression. Now children, after that you've been told that there is height of the balloon, right, which has to be found out. Now in order to talk about the height of the balloon, what we require to do is we require to draw a straight line from the top vertex, and it has to go up to the horizontal, and this straight line actually is going to depict the height of the balloon, right? So this is a little tilted. There should be an exact angle of 90 degrees between this straight line and the horizontal. So as such, let's consider that this is that straight line, and now the length of it has been given to you to be something that has to be found out, so we will assume it that it is h, right? Now children, there's another assumption that you require to do, that is, let's consider that the distance of the first kilometer stone S1 from the foot of the perpendicular drawn from the balloon is, say, x. That means if we talk about this distance, let's consider it to be x, obviously, as the other distance is the one which can be subtracted from 1, the value x. So the rest of the distance can be written as 1 minus x if we consider the distances to be all in terms of kilometers, right? So now children, we have our right angle triangles ready. Is it? Yes? No, it is not, because we've yet not taken the angles within our right angle triangles. So the next thing that we're going to do is we will bring these angles within, and since you know that if you talk about this straight line and this straight line, they are parallel to each other, as such both of these are going to be alternate interior angles. As such, this angle will be alpha, and similarly this angle is also going to be beta in a similar way, that is by alternate interior angles. I'll quickly remind you, this is a straight line which is parallel to another straight line like this, because this is the horizontal and this is a line which is parallel to the horizontal, right? And this acts like the transversal, so both of these angles become equal, which are alternate interior angles, just like in this case. Okay, now children, we have two right angle triangles, as you can see. So what we can do is we can name the foot of the perpendicular to be, say, some point capital P, right? And now further, we have two right angle triangles here. So we'll talk about the first right angle triangle, that is in the triangle BS1P, right? What do we have? We have here that tan of alpha can be written to be equal to perpendicular, which is h, which is divided by the base, which is how much? Which is x, right? So this as such will become the first equation, children, and after this now we'll be talking about the second equation, where we will jump over to the second right angle triangle that we have, that is in triangle BS2P. Okay, so in BS2P, now when we talk about, we can again talk about tan. So we talk about tan beta, right, which becomes equal to, again, perpendicular upon base. Perpendicular is h, children, here, and base is how much? Base is 1 minus x, because as the distance between both of these kilometer stones is 1 kilometer, and since this distance has already been marked to be x, so the rest of the distance will be 1 minus x, right? So children, now this is the second equation, and now next what we do is we will now be talking about trying to find out the height of the balloon, right? So in order to find out the height of the balloon, we require to make h the subject of the equation. For that, we have two equations and we have two variables, considering that alpha and beta are known constants, that is, known values of the angles of depression. So children, from the first equation, what we can say is we now have here h, right, upon x, which is equal to tan alpha, and as x is to be made the subject of the equation, so x can be written to be equal to h upon tan alpha, right? Now children, here we will be using this in the second equation to be able to get 2h. So now we talk about the second equation, and in the second equation, children, what happens is we now have here the value of tan beta, right, which is equal to what? Which is equal to h, which is divided by 1 minus x. So here further what we do is we now keep this value of x, that is, we have tan beta, right, which becomes equal to h divided by 1 minus, what is the value of x? We just found out the value of x to be h upon tan alpha, and that is what we keep here. And further now, next what's going to happen is we have to try and make h the subject of the equation, as that's the height of the balloon. So the next step, children, here in the denominator we will be taking an LCM. As such, this is h, which is divided by tan alpha, right, minus h, where the LCM is tan alpha. Right now, children, as this is one fraction which is divided by another fraction, we know that the whole denominator sign is here, right? So in place of writing this whole denominator sign, we can replace it by the division sign, and after that we can convert it to the multiplication sign. So this is actually h, which is divided by tan alpha, right, minus h, and further divided by tan alpha, right? So for the children, in the next step, what's going to become is this is going to become equal to h, which is going to be multiplied by tan alpha, and in the denominator we have here tan alpha, from which h is subtracted, and on the left hand side, children, we have tan beta. Right now we are in a position to cross multiply. As such, we now have tan beta, which is going to be multiplied with tan alpha minus h, right? And further on the right hand side we have h, which is multiplied with tan alpha. Right now, children, we'll keep the terms with h on one side of the equation and the others on the other side of the equation. Now multiplying this tan beta within, so we have here tan alpha, which is multiplied with tan beta, and from that is subtracted h times of tan beta, as tan beta is going to be multiplied within. And now, children, this is equal to h times of tan of alpha. Right now, what we do is we can keep tan alpha and tan beta on the left hand side, and on the right hand side we have h tan alpha, right, to which is added h tan beta. Right now, children, here what we do is, if we take this h to be common outside, inside we are left out with tan of alpha plus tan of angle beta, and on the other side, children, we have tan alpha tan beta. Right, so we've almost reached. Right now we make h the subject of the equation. As such, here we have tan alpha tan beta, and in the denominator we have tan of alpha plus tan of beta. Now we quickly go and check whether this is exactly what you were required to bring or not. Okay, tan alpha into tan beta, this dot actually stands for multiplication sign, right? So we have tan alpha into tan beta, and in the denominator we have what? We have tan alpha plus tan beta. This is tan alpha plus tan beta, and therefore we can say that we've been able to prove the sum. Therefore we can say that proved. Right now, children, all of this I will quickly discuss so that if there is any doubt withstanding, all of that gets cleared. In the question, children, you've been told that there is a balloon, right? And what's happening is, in this balloon, right, there is probably an observer, right? And if suppose the observer wouldn't have watched, then probably you wouldn't have had this question. So obviously that person is perceiving these 2 kilometer stones, and I can tell you there must be something special that that person is watching, or probably a person who is sitting on 1 kilometer stone and another person who is sitting on the other kilometer stone, and what they are doing is what is not known. Okay, so there is this balloon, children, and now we have this 1 kilometer stone, and this is the 2nd kilometer stone. So obviously the distance between both of these stones is going to be how much? It's going to be 1 kilometers. And further here we've been told that if from the first balloon the 1st kilometer stone is seen, then the angle of depression is alpha, and the 2nd kilometer stone, if it is watched from the top of the balloon, the angle of depression is beta. So what is the angle of depression? It is the angle with the straight line joining the eyes of the observer to the object makes with another straight line which has been drawn from the eyes of the observer parallel to the horizontal. Right now, children, these angles can also be brought within the right angle triangles, as you know that this straight line and this straight line are parallel to each other, and thus this will be a pair of alternate interior angles which will be equal. So this angle is going to be equal to this angle in a similar way. Now, children, we drop a perpendicular from the balloon to the horizontal surface, and this gives us the height, and we consider the height to be, say, some h. Now we have to prove that that height actually is this expression. For that, we go ahead and talk about the first right angle triangle, where we have tan alpha to be equal to perpendicular upon base, that is h upon x. Now in the second right angle triangle, we have here again tan beta, which can be written to be equal to perpendicular, which is h, and base, which is 1 kilometer, this complete distance from which x can be subtracted, right? That is this. Now we use the first equation and find out the value of x in terms of h. Now in the second equation, we substitute this value of x where x comes. So as such, we have tan beta, which becomes equal to h, which is divided by 1 minus, now in place of x, h upon tan alpha. Now further, as there are fractions, so we take an LCM. The LCM becomes equal to tan alpha, and here we have tan alpha minus h. Now as this is one fraction divided by another fraction, so the whole denominator sign is here, the division sign. So further, we write it to be the division sign so that we can remove some confusions, and then we can convert the division sign to multiplication sign. And after that, then we write the reciprocal of this fraction, that is, we have tan alpha, which is divided by tan of alpha minus h. Now next, children, we cross multiply, and then we get an expression on the left hand side, and further we find out the product, and then we keep the terms with h on one side of the equation, and then further take h to be common outside and keep the rest of the terms in the denominator, and thus we are able to get to the value of h, which is the height of the balloon. And children, this is the expression that you were required to bring, and therefore this stands to be proved. So is everybody clear about this? So if there is some expression whose value you don't know, right, that means it is dealing with constants like ABC or alpha, beta, gamma, right? They are not your normal angles like 60 degree or 30 degree. Don't be scared. Just go about it the same normal way. I know that you're strong in maths and you will be able to do it. So make sure now, children, that you've understood. Do the sum once more, right? And then you'll be able to understand this concept really well. Moreover, if you've been here till the end of this lecture, you should be getting some gifts. For that, if suppose you have a problem, you can directly write to me. For that, there is a form link. Tell me what your problem is and I'll solve your problem. Moreover, there's also a shot which is linked with this, and that will actually tell you how you can understand the angle of depression. These shots are very useful during your examination. Make sure you keep working hard and tell me what your problem is, and do comment as to what is new that you learned and who could have been, say, on the balloon and who probably could have been below, right? So let's make maths fun and easy to learn. Stay in touch, keep working hard. Bye. Make your maths strong.